Hi guys, hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In my discussion today, I'm going to look at the concept of complex numbers. Now we have come across this specific name in our previous discussion on the concepts of different types of numbers and how we can treat them. But of course, in some of our explanation on the different types of graphical methods which we have dealt with, of course, we have come across this specific term. And I'm going to be basically considering developing a particular range of steps which are going to be assisting us try to basically define this aspect of a complex number. And from there, we're going to see various ways in which we can particularly represent this aspect of complex numbers in terms of graphs. And that's going to be forming a basis for us in trying to, of course, represent these numbers on what we refer to as the Gandhi diagram. In this particular video, I'm going to use a particular example of an equation which is going to be given in terms of this specific quadratic equation. And this is going to be assisting us trying to define a concept of a complex number by trying to solve for the value of x. Now, we had said that we can use different methods in trying to find the value of x for such a kind of an equation. And one of them was, of course, completing the square method. Now, from basic geometry, we know that a square is a regular figure that consists of four different, of course, four equal sides. And in this case, we are going to consider having to find the factors of this specific right side of the equation, and of course, which is going to be assisting us trying to, of course, manipulate the equation and try to come up with specific factors which we are going to consider from this particular equation. Now, in a sense, this is going to be using this particular strategy which we have been using for finding of course, the factors of this particular square. I suppose we have this specific equation, which is going to be a general representation of a quadratic equation. Now, we're going to see that a, b are going to be coefficients and c is going to form our constant. And we're going to have this equation rearranged in a form of x squared plus bx. Now, for us to find this specific aspect of a c in this left side of the equation, we're going to introduce another, of course, a constant which is going to be given in terms of ax squared plus bx plus c. Now, our c in this case is going to be half the value of this specific coefficient for b and the square of that. And we're going to do the same operation on the right side of the equation and have it given in terms of b all over 2 the square of that. Now, this strategy is going to be assisting us trying to find these specific, of course, factors for that particular square. Now, in a sense, this is going to be appearing in a form which is going to be giving us those specific squares. Now, therefore, I'm going to perform this particular operation whereby we're going to have x, the equation rearranged as x square of that one plus x. Now, the second part of the equation is going to be having a coefficient of b equivalent to 1. And therefore, I'm going to have this specific representation of the equation given in terms of a -1 by taking this over the equal sign. And therefore, we shall have this one given in terms of x plus a half the value of this one, which is a half b. And then we shall have to have this specific operation similarly performed on the right side of the equation, which is going to be giving us this specific representation. And therefore, in our case, we are going to have x plus a half forming a square of this specific nature. And of course, this is going to be the square of the two factors. So therefore, we are going to have this one given in terms of positive. So this is going to be forming a quarter. And therefore, x plus a half, the square of that one is going to be representing -3 all over 4 given as such. So for us to find the value of x and a half, the sum of that, this is going to be taking the roots of the two sides, and therefore we shall have this one is -3 all over 4. Now, according to the laws of Saxon, which we have learned from our previous videos, we have said that we can have this one represented in terms of a -1/2. So I've taken this one to the other side of the equation, and the value for the root of this specific representation is going to be given in terms of positive or negative, the value of -3 all over 4. So this is going to be given in terms of a half positive and negative, the root of a -3 all over 4 given as such. So if I just, so this is going to be all over 2, whereby we'll have evaluated the specific roots for the, of course, a denominator of this specific function, which is part of the equation, which is all of it is over the root sign. And therefore, we shall have this specific value. So we can consider having the common, of course, denominator for this value, whereby we're going to have the first term given as 1, and the second term is going to be given in terms of I, the root of positive 3 given as such. So this is going to be representing x. But if we try to look at this specific equation, I've just introduced another specific notation or denotation, which is going to be given in this specific order. Now we're going to be looking, of course, deeply into the works of Leonhard. So this is going to be Leonhard Euler. Now the works of Leonhard Euler are going to be assisting us in trying to interpret this specific annotation which I've just given. But this basically is equivalent to the root of a -1 given as such. Now we have basically looked at this work particularly on the concept of the Euler's number, which I've done extensively in one of our videos, which is basically equivalent to 2.718, which is going to be seen widely applicable in various aspects of course, differential and integral calculus on different areas of especially exponential curves for the exponential growth and exponential decay curves, and other areas which we're going to come across, especially in logarithms. Now, in this particular case, we are going to see that this specific representation of this particular root of, or rather the square of this specific, or the value of x, is going to be assisting us and trying to create an emphasis on this specific representation of the number which we have given in terms of the root of a -1. And therefore, that's going to be opening for us a way of representing what we call complex numbers. Now, in this case, I will have this one given in terms of perhaps a statement form, which is going to be giving us a definition of what basically this aspect of complex numbers are. So we are going to have a complex number, or perhaps a definition, which is going to be having as for us a complex. So we can have this one given in terms of a complex number is defined by a phasor. So we have talked about the phasors. A complex number is defined by a phasor, which is going to be given in terms of x plus I y. Now in this case, I've just introduced this specific aspect of I from my previous, of course, discussion, which we have done an evaluation of a quadratic equation. And this is going to be giving us this specific representation which we have had for the root of -1 given as such. Now, a complex number is going to be consisting of this, of course, two specific sections which we have given in terms of x plus I, y. Now, from our previous discussion on the concept of of course, the Cartesian coordinate system, we had said that we're going to have for a two-dimensional representation, we're going to have x and y components given as such. Now, for a phasor, which is going to be consisting of course, the values of x and y given as such, we're going to assume that this basically is a representation on the, of course, what we refer to as the Cartesian coordinate system. And this is going to be forming our phasor, which is equivalent to x plus I, which is a complex section together with this specific aspect of y. But we're going to have special names which we are going to consider for the x component, which is going to be referred to as a real component. So this is going to be forming a real component of the phasor z given as such. And this can be abbreviated in terms of the real component of z given in terms of course, re into the phasor of z given as such. And this specific section for the imaginary part is going to be given in terms of this particular imaginary. And it's going to be abbreviated using im, of course, into z given as such. So this is going to be forming our specific representation for the, of course, concept of a complex number on the graph. And these are going to be the specific terms which we're going to use for the imaginary, of course, part on the y-axis, and the, of course, the real component, which is going to be on the z-axis, are given as such. So in this particular case, we're going to see that the particular variables which we consider for the imaginary and real components, which are going to be given as x and y, are going to be a set of real numbers, and we're going to treat them as such as we come across them in our various discussions. So conventionally, we're going to see that this specific aspect of x and y components can be given using those specific, of course, abbreviations which I've just given. And the component which I mentioned over I is equivalent to the root of 1 in this specific case that has been included in this representation for the complex number is referred to as an imaginary unit. So in this case, in case we come across this specific representation, or if I mention the concept of an imaginary unit, and therefore it's going to be representing this particular case. So I'd like us to be remembering this specific definition and reference for the concept of a complex number. In case we come across it, then it's going to be more elaborate for us in what basically this specific aspect of a complex number represent. Now, in our subsequent video, as I said, we are going to be showing ways in which we can represent these complex numbers in form of what we refer to as the Argand diagram. And I'm going to be giving specific examples of these specific, of course, equations which we have given in terms of the phase of z equivalent to I, y given as such, and other range of values perhaps which is going to be constituting some of the imaginary equations and some of the basic, of course, operations which we can perform on them. So kindly check our description boxes for various links of other videos. Engage us in the comment section and also ring that notification bell. Do not forget to subscribe, and also, of course, I kind like to request our members to be checking a link that I normally put in our description box. It's going to be having a range of videos which are going to be, of course, in terms of our playlists, and these are videos under the same topic of our discussion. So that is it for now, guys. Bye, God bless you. Catch us in our next video.